Hello, welcome to the NPTEL course Fundamentals of Composite and Cellular Materials. The topic for today's lecture is additive manufacturing for fabricating cellular materials. In the last few lectures, we have been discussing on the various processing techniques for fabricating porous materials. We started with the processing techniques for porous ceramic fabrication. Then we discussed about the various techniques for metal foam or porous metal fabrication, and in the last lecture we discussed about polymer foam fabrication. In the last lecture, the main topics that we discussed about were the various techniques of polymer foam fabrication, various classifications of polymer foams in terms of their hardness, density and bubble structure, and we also learnt about the current problems in the polymer foam fabrication and the possible solutions to those problems. In this lecture, we will discuss about additive manufacturing techniques for fabricating porous materials. We will learn briefly about the various AM techniques, and also we will learn about two main topics of AM for cellular materials fabrication, that is, one is geometrically defined lattice structure porosity or GDLSP, and the second one is geometrically undefined porosity or GUP. The main keywords for this lecture are additive manufacturing, porous materials, GDLSP, GUP, inkjet 3D printing and selective laser sintering or melting, that is SLS or SLM, and laser engineered net shaping or LENS or LENS. To start with, as we know, additive manufacturing or AM is a modern technique, and which has actually become very popular all over the world for its many advantages. ASTM defined additive manufacturing as a process of joining materials to make objects from 3D model data, usually layer upon layer, as opposed to subtractive manufacturing methodologies. Now, this definition has many sub definitions or subtopics which needs some attention. To start with, it is a process of joining materials. That means, AM can be thought of as a variety of the welding process or joining process, where individual layers or individual coatings are actually joined together. Then it is actually made from a 3D model data. That means, this AM technique actually starts with the creation of a 3D model or a CAD drawing of the actual final component to be fabricated, and then usually this fabrication is done layer upon layer. That means, this 3D CAD model, once it has been fabricated, the next step is to slice the 3D CAD model into individual 2D layers, and these 2D layers are actually deposited one upon another, and after one layer has been deposited, the table or the platform on which the AM component is being built, it actually moves downwards by certain amount of thickness or distance, and the next layer is deposited. And this has certain, and this is a big difference with the more conventional subtractive manufacturing technologies like casting processes. AM has many advantages which include lower startup cost. That means, the initial startup cost is rather low, although there are techniques like laser processes or electron beam welding where the initial startup cost could be pretty high. It also has reduced raw material wastage. This is a big advantage of AM, because here the final component is already designed by the CAD model, and then this is actually built layer upon layer. That means that the final component after the build up is actually saves a lot of material, because we do not need to scrap material or cut out the things after it has been fabricated. So, in this way AM actually provides a much lower material consumption. Ease of customization, because in this case we actually fabricate or actually design the initial model, and then this actually provides a very wide range of customization. Also, the dimensions and the shapes of the component can be varied, and it is also possible to fabricate very complex design shapes with AM techniques in a very easy fashion. The high speed of the development process from prototype to production, that means it does not take a long delay between the CAD model fabrication and the final composition. So, it can be it is quite fast process. It actually consumes less amount of energy because the number of process steps are much reduced over here, and we also have very less amount of overall material loss, and that is the reason that the overall energy consumption in AM techniques are much lower than the more conventional techniques like casting, and also we can use low volume production runs. And all these reasons or all these advantages actually have made additive manufacturing a very useful and powerful technique for current fabrication methods. And also there are examples where cellular solids or porous materials are often fabricated these days using AM techniques. So, again this main flowchart that is involved in the AM fabrication process is shown over here. As I already mentioned, it starts with the CAD model. That means first the CAD model is created of the component to be done, and then this CAD based model is actually sliced into individual 2D layers. That means this actually, and this information is actually fed to the computer, to the main fabrication system, and then we come to the part being in this stage where actually this 2D model is actually fed on the design, and then by some technique, by either laser deposition or some technique, this actual material or the powder, or it can either be a powder bed or it can also be like a powder deposition, it is fed on the platform, and then this whatever this deposition is actually follows a predefined path to actually create the final design. And then once one layer is complete, the table or the platform actually moves down by one certain amount of thickness, which actually corresponds to the individual layer thickness, and then the same process is repeated. That means in one process step this deposition is created, and then after it is completed the platform moves down by the predefined amount of thickness distance, and then the next layer of deposition is again created. And in this way this process continues until the final part is completed, and then many a times, especially for ceramic materials, it requires sintering, as we know that without sintering the green body does not have sufficient strength, and for that after the part being finished and we obtain the final fabricated part, the 3D object. And the big advantage in this case is that the 3D object actually has a very well defined geometry, and actually it mimics the initial CAD model which was created for the material for the actual component. Now, in terms of, as I already mentioned and as we all know, AM techniques are these days very often used for fabricating many kind of materials like ceramics, metals, composites and so on, and these AM techniques are also very often used these days for fabricating cellular materials with very well defined porosity and pore morphology. Now, fabrication of AM components or AM porous materials has actually two different domains. The first domain is called GDLSP or geometrically defined lattice structure porosity, and the second domain is called GUP or geometrically undefined porosity. That means the names itself, they actually tell that what they actually mean. The first classification of the GDLSP, actually this means that this actually provides the well defined geometry. That means once the 3D model is created at the very first stage, at that stage itself we have to actually determine whatever the porosity and the pore size and the other structural parameters, and the AM technique will actually fabricate the component based upon the definitions which were created at this stage. That means we can actually assume or state that this GDLSP process or the GDLSP state is actually kind of more of a design controlled parameter where we actually control the design. The second process or the second stage is called the GUP or geometrically undefined porosity. That means in this case the porosity that we obtain, actually these are not controlled by the initial design. That means this second stage, as we will see afterward, the pores that we obtain in the cellular materials in this stage are actually controlled by the process parameters, not by the design parameters. So, again we can differentiate that GDLSP, the pores are design controlled, whereas GUP, the pores are process parameter controlled. Also in GDLSP, because the pores are our process pores are design controlled, we can actually fabricate a wide range of porosities. At the same time, we do not really go to very fine porosities, because those are again difficult to fabricate. So, typical pore size for GDLSP is between 100 micron to 1 millimeter, whereas in case of the GUP process, where the pores are formed because of the process parameters, in those cases we can actually obtain much smaller amount of porosity, that is up to around 1 micron or in that range. That means what we have to understand is that the total porosity of the fabricated part after AM technique is actually a combination of these pores from GDLSP, that is design controlled, and the pores from GUP, that is actually our process controlled. Now, we will briefly discuss about these two techniques, this GDLSP and GUP. This GDLSP, as we already understood, this is about the design. That means our design process will actually control how much amount of porosity we have and what will be the pore dimensions and pore morphologies. That means we can very precisely control the pore size, shape, porosity, and also in that way we also control the permeability to whatever range we obtain or we require. And these kind of GDLSP pores are very optimum for many applications where we require very well defined pore structure, such as biomedical applications or applications as filter or catalyst. Now, the development of the 3D printed GDLSP structure basically have three different steps, as we will show in the next slide. So, as you can see over here, the first stage in this GDLSP process is actually the definition of the unit cell topology. That means we have to identify or define at this stage what will be the basic unit cell of our 3D component, of the final component. And this is a very important stage, because these will actually control many aspects like the property, and also in case of your biomedical applications and also for filtration, the permeability will depend a long way on this unit cell topology. After we have defined the unit cell topology either as cubic or rhombohedral or many complex like dodecahedron or whatever, the next stage is the specification of the porosity. So, because our aim with this AM technique by GDLSP is ultimate to fabricate a porous material, that means you will see afterward that for the porous material the most important property is the amount of porosity. And after we have defined the unit cell topology for our process, the next step or the second stage is the specifying the porosity. And this is typically done by controlling the dimensions of the struts or the ligaments. That means we can assume these as our struts. That means in this case we have a cuboid shaped unit cell, and the individual dimensions of the arms or the sides of the unit cell are actually controlling the amount of porosity. That means if we want a low porosity structure, we have to make the unit cell or the struts thicker, that will give a lower amount of porosity, while if the struts are thinner, we will actually obtain a higher amount of porosity, which will again control the mechanical properties and also other properties. Because you will see afterward that this porosity, that means the strut thickness and all those things will have a significant influence on the thermomechanical properties and other properties, and this way by controlling the strut dimensions and their length and thickness, we are actually controlling the properties of the final material through the control of the porosity. And then the next stage and the final stage is the desired pore size and to ultimately build the component. That means once we have identified the unit cell topology and its specified porosity, that means we have identified the dimensions and thickness of the individual unit cells, the next and final stage is to repeat this in 3 dimensions to our desired final end component. So, this is actually this all three steps together, these actually give rise to our GDLSP, that means the designed control porosity of the final AM component. And again this flow chart is typically followed, that means we can see over here in this process, again first we have to identify what kind of porous structure we want to fabricate, because these days it is possible to fabricate the porous structures out of metal, ceramics and polymers by additive manufacturing technique. That means we can actually apply these techniques to all these kinds of materials. Definitely we have some limitations depending upon the individual material properties, but in general we can apply these AM techniques for fabricating metals, ceramics and polymers with substantial amount of porosity. And after this once we have identified which metal or ceramic or polymer to be formed or to be fabricated by AM technique, the next question to be asked is what kind of porosity and how much amount of porosity we have to generate. That means there comes the question whether the pores to be mainly lattice structure pores, that means this GDLSP pores, or the pores will be more like the GUP pores, and then depending upon that we have to control the individual techniques or processes of the AM techniques which will actually yield our final component. Now, after this basic idea about the GDLSP pores, next we have to learn, or we should learn briefly about the GUP or the geometrically undefined pores. That means we already learned that the GDLSP pores are basically design controlled. That means the amount of porosity is not dependent upon the process parameters, rather it depends upon the selection of the unit cell and its parameters like how thick the struts are, how long the struts are, and how much or how many of those repetitions are there in the 3 dimensions, and these will actually control the amount of porosity in the GDLSP process. In case of GUP, as I have already repeated several times, it is not about the initial design. Definitely design will have some effect, but the main effect will come from the process parameters. And how? This we will see for 3 different AM techniques which are commonly used for fabricating porous materials. This is one is the inkjet 3D printing, the next one is the selective laser sintering or melting, this is SLS or SLN, and the last one is the laser engineered net shaping or lens technique. Now, this slide basically shows the schematic of the inkjet 3D printing process, and as we know, this inkjet 3D printing was one of the first AM techniques to be established worldwide for fabricating bulk components. The schematic of the process is shown in this slide. So, as you can see over here, it starts with, again we start with the initial definition or the initial model creation of the 3D component, and then we have this after this is created, we actually deposit these binder materials and support material as a form of liquid droplets on this platform. And after, as I mentioned, after this one predefined layer has been fabricated, this platform actually moves down by this predefined thickness and the next layer is actually deposited. So, this is actually the basic process of the inkjet 3D printing process, and again we can actually precisely control the porosity and the pore morphologies by this technique very well. This technique, as we will again see also for the other techniques, we can have 2 different kind of pores, that means the macro pores and also the micro pores. Again these macro pores, these are again the GDLSP pores, because these are the pores which are developed through the design. That means when we design a 3D component, that means if this is a 3D component, for example, just like these cells are drawn side by side, and then for example these are the individual struts are there, if we assume something like that, then all these pores, these are the macro pores and these are our GDLSP pores. But however, because we are doing this fabrication depending upon the process parameters, there will also be pores remaining over here. That means between the struts there will also be pores remaining, and these pores, these are depending upon the process parameters, and these fine pores which are remaining in the struts, not the large pores between the struts, these pores are called or known as the micropores, and these are the GUP pores. After this 3D printing, another technique which is very often used for fabricating AM components or cellular materials by AM component is selective laser sintering or selective laser melting, SLS or SLM. This SLS or SLM technique has actually also become very popular for fabricating bulk components. So, again the main process is being shown over here. Again the main process starts from creating the 3D model of the actual component. That means, we see over here, just like we saw in the initial process, we initially create a 3D model. In this case, again this lattice structure or lattice cuboid structure has been fabricated, and we predefine the strut thickness and other design parameters. Then this powder or whatever powder to be used for fabricating this porous material is actually laid on the table, and this laser beam is actually moving around on the powder bed, following the initial design which has been fed to the system. And after the initial layer has been deposited, this again the platform actually moves down by one layer, and again next layer of powder is fed, and this whole process is repeated until we obtain the final stage. And in many cases, especially for ceramic fabrication, after we obtain the green body in this way, the green body needs to be sintered to obtain sufficient strength in the porous material. Now, this technique, this SLS or SLM technique can also be used also for with electron beam technique also, like this deposition process. Now, in this case, depending upon the process parameters, we have the various formation of the micropores or the GUP pores. There are many process parameters which need to be controlled. This is one is the hatch distance, then bed temperature, layer thickness, and laser energy density. So, these are all the parameters which actually control the amount of micropores or the process parameter induced pores in the final structure. Among the parameters, as we learned, this one is basically the layer thickness, or so the more or the higher is the layer thickness, there is actually more chances of porosity formation. Also, there is one important parameter is the laser scan speed. If we increase the laser scan speed, that actually means that for the same amount of laser energy, we have the energy density or heat input will be reduced, and that will also provide a higher amount of porosity. Also, hatch distance, that means if we have multi-track depositions, then the hatch distance can be defined this way, and this hatch distance can also control the amount of porosity from this design from this process control. If the hatch distance is smaller, that means if we have less amount of distance between two depositions, there will be higher amount of overlapping between individual depositions, and this more amount of overlapping will actually result in reduced amount of porosity. That means, if we increase the hatch distance, the amount of GUP pores will be higher, and if we reduce the hatch distance, the amount of GUP pores will be lower. So, all these parameters, like if we that means once we know that which component we have to fabricate and with how much amount of porosity, we have to control all these process parameters in a very efficient manner to actually obtain the final end porosity that we actually want in our final component. Another process, a very similar process, also employing laser to fabricate the porous materials, is being shown over here, but this process is called laser engineered net shaping, or it is also called direct energy deposition. In this process, in comparison to the last process where the powder bed is created, in this case there is no powder bed created. In this case, actually the powder or whatever material powder we need for our component fabrication is actually coaxially fed onto the substrate with the laser, and we also have some gas shielding to actually overcome the oxidation problems. Again, in this case, the initial process is that we have to first create a 3D model or CAD model of the component, and then using this lens DED or direct energy deposition, we have to first deposit one layer directly or exactly following the dimensions and the shapes of the initial CAD model, and once this is done, the platform will actually move down or go lower by certain amount of distance, and then the next layer will be deposited. So, this way it is a very similar process, only difference is that in this case we do not use any powder bed, rather the powder is actually fed coaxially with the laser being used. And also in this case we have the process parameters which actually control the amount of porosities, and these are again similar process parameters like the H distance, laser power, scan speed and feed rate. So, all these controls parameters will actually control the amount of final porosity in the final AM component. That means, it is very important that once the before the final component is fabricated using laser, using these AM techniques, one needs to actually optimize the process parameters very precisely, because otherwise if the process parameters are not optimized, the amount of GUP porosity will actually be much higher, and that might actually lead to very undesired properties, because we have to also understand that the more this, because these GD-LSP pores or these design control pores, those are actually controlled or designed based upon the final application or intended application. That means, be it a biomedical application or be it for filtration, these pores are actually intended pores which will give the material or the final material its intended functionality. However, these GUP pores, they are often not planned, and we always aim to reduce these pores, because the presence of these pores in our component will actually render the component to become weak, because these will actually, if the pores are in the arms or on the struts, they will reduce the strength of the struts, and that is never intended. That means, the exact process control is very important to actually obtain a porous material with good properties. So, again in this slide, we have discussed about the various parameters which actually control the amount of porosity in the various techniques in 3D printing, in SLS, SLM, lens and EBM. EBM is electron beam welding, and all these parameters we need to control very precisely to actually obtain the final amount of porosity and the final properties that we intend in our final structure. So, here actually I show some recent work. You can see these works are from very recent publications from this year, and these are again very nice lattice structures have been created, as you can see over here, by 3D by these additive manufacturing techniques. And as you can see that as we move from the left hand side to the right hand side, these GD-LSP pores, they are actually becoming finer, and these are all done because the initial CAD model was fabricated according to that. And these structures, the main benefit of such structures is that such homogeneous and uniform structure is actually not possible with any of the other techniques for foam fabrication which I discussed previously. There is another example you can see over here. This is another example where there is a pore, there is a body for biomedical application, and we can see that in the initial in the figure A, we can see those micropores, again these lattice structures with different amount of GD-LSP pores, and then as we go to we can see that these individual struts, they have very well defined geometry, they are very regular in shape. And also if we see the microstructure, there we can see that these are the small pores, because these pores what we obtain over here after the final sintering, these fine pores in image D or image E, these are actually the GUP pores which we are unable to control, because these actually depend upon the amount of final sintering. That means, it depends upon that how much, that whatever the sintering atmosphere, how much was the sintering temperature and time. So, all those parameters will actually control this geometrically undefined pores. So, to conclude, we learned that additive manufacturing is a very powerful technique for fabricating porous materials, as it is also used for other bulk materials. For porous materials, additive manufacturing techniques can be classified into GD-LSP or geometrically defined lattice structure porosity, which are the design control porosity, or GUP pores, which are the geometrically undefined porosity or the process parameter controlled pores. And we also learned that these GD-LSP pores actually render the material its functionality, while the GUP pores can actually make the material more weak if they are not controlled in a proper manner. And we also learned that there are various AM techniques that can be employed for fabricating many different kinds of porous materials. These are the references which were used for this lecture, and in the next lecture we will learn about some classification of cellular solids, and we learn about the amount of cellular solids, the pores, and how to actually characterize the pores, their shape, size and topology. So, with this we come to the end of the chapter for fabrication of porous materials, and from the next chapter we will start about the characterization and properties of porous materials and how they depend upon many of the process parameters and porosity and pore morphology. Thank you very much.